I think you can see my screen now.
Yes, sir.
Yes, sir.
Yes, sir.
All right. So today our main discussion is controller implementation. Um, by now, you have learned a lot of things about control systems, right? Uh, even you can design and simulate a controller for a given plant, but all in on paper and in MATLAB. Okay, but you might wonder how this is physically implemented using a electronic circuit board. How can you put all these equations, the block diagrams, MATLAB, the body plots, and things like that onto a real hardware so that you don't need MATLAB or a computer to control a system? If you go out there and see the plants, machineries, you can see the computers there. Of course, they are there. That is in order to monitor complicated systems, right? And that kind of high level management, configuration kind of operations. But if you go to a low level controllers, right, you don't see a computer there. It is basically done by an electronic control board, right? So you might be very curious to know about how we can bring all these equations, right, and whatever we do in MATLAB onto hardware, right, with or without software. Uh, so that is the major concern today, and therefore the title of the subject, the lecture today is analog controller implementation. So it's very natural that the natural progression from theory to practice is analog controller, not the digital one. I will get on with digital one little later, but for the moment, to let you know what these different entities are, how they are related to each other, I would say this about digital controllers. It is basically another way of implementing the analog controller. Okay, but everything that is happening within a digital controller is essentially what is happening in the analog controller itself. There can be slight deviations because of the analog digital fundamental difference, right? Other than that, the digital control is also trying to do the same thing that the corresponding analog control is doing. So from theory to practice, the first one is basically analog controller. Okay. Now let's look at a control system. So here you can see the actuator and a plant. Okay, I actually put them together. All right. For some of you, maybe still having confusion with this one, I would say this. The plant is basically the plant where you have some components, right, in order to produce an output. But the plant is also attached with the actuator. Like, for example, if you look at a boiler, the actuator is the heater. Okay, it is part of the plant. So therefore, it is okay to say actuate and plant together. So the actuate is controlled by the control system. So there you can see the controller, right, before the plant. So the controller controls the actuator, and as a result of that, the plant get changed, right? So that is how things happen. Now our focus is onto this controller here. Now recall your memory about the few controllers we dealt with so far, right? We looked at PID, we looked at the servo loop tuning, shaping, right? Using a lead compensator, lag compensator, gains and all. So what is common in all these controllers? What is common in all these controllers? If you follow a PID path, if you follow the loop shaping path using Bode, if you look at just feedback gain and some sort of very simple structure, once you develop the controller, they will have the common shape, and that is this. Controller is U over E. U is the actuator signal or the control signal here, U, and E is the error. So from one hand, the controller receives the error, and on the other hand, it commands the actuator. Okay. So when you get this ratio here, US over ES, almost always you get something like this. That is known as rational polynomial of S. The rational polynomial of S. So you can see the numerator polynomial of S, denominator polynomial of S, where the denominator is of higher order, equal or higher order than the numerator. Right? Whether you follow PID or otherwise, right? When you write down the controller, it is one polynomial of S as the numerator, another polynomial of S in the denominator. So when you want to implement a controller physically, now you know what you need to do is to figure out a way to implement a rational polynomial of S on real hardware, actual hardware. Understand? So this is problem solving, not customized or specific to control system, but in general, engineering problem solving. That is the path we follow right now. We look at what we have, that is the controller, and we understand it is a rational polynomial of S. Now, what is the problem? The problem is to build an electronic circuit board to control the plant. So now we know, therefore, what we need to do is to find out a way to implement this rational polynomial of S on real hardware. Okay, so it should be very clear to everyone whether we have a solution or not is a separate issue, but we are very clear in our mind that this is what we have to do. Okay, right. To ease up the situation a bit further, I would cross multiply this equation, the controller equation, like this. Okay, so US multiplies with this denominator polynomial here, ES gets multiplied with the numerator polynomial here. So then it becomes like this. Okay, and then I isolate US over here. This is the control signal output, right? And I put all the other terms to the right hand side and prepare this one. So take a minute to understand these contents, right? This is the generic content of controller implementation. So on the right hand side, now you see error and control signal, US in Laplace domain, and on the left hand side, it is US. Okay. So this is what we need to implement on real hardware. Now, for those who have done signals and systems, would say this kind of equations we call as infinite impulse response filter. Right? Then you connect this one to something you already know. So it makes you feel comfortable about uh, the task at hand, dealing with infinite impulse response filters. And if you look hard into this equation, you will see, let's take the first term here. What do you see? ES times AM. So just a gain, right? Multiplication. So ES is the error if you look at the time domain, because whatever controller that you implement, right, on real hardware, it can take uh, uh, actual signals, right, in this world, time signals. It cannot take Laplace, right, as it is. So Laplace is, again, we use to simplify the process. But you can't have Laplace signals in the real world and use it to command an actuator. No, you can't do that. You have to use time signals. So therefore, if you look at the time signal here, this is the error basically. You multiply error with a gain. So in the real electronics, you need to do this. Is there a way electronically to implement this multiplication? And then what you have next is actually S term, S times ES with a gain. S means differentiation in time domain. So you need to differentiate error, right? Now the error is a continuous signal. It is changing all the time. It's like a wave, continuous wave. So you need to calculate the rate of change of error. That is the term which is over here. You differentiate and then multiply. So then if you go on, proceed like that, you will see you have to multiply, differentiate again and multiply with again. Differentiate and multiply, differentiate, multiply, differentiate. This is the chain process that you need to do if you want to implement this on actual hardware. You need to be able to get the error signal and directly multiply it. That is the first term, and after that you have to differentiate, multiply, differentiate, multiply, differentiate, multiply. Every time you do that, differentiation, multiplication, you have to add these intermediate uh, results, right? This is the summation of all these terms. And if you look at the other term here, US is the control signal, which is also changing, right, as a continuous signal. It goes up and down, positive, negative, right? So what you need to do is differentiate, multiply. You can see over here, S times Bn minus 1. So this is, again, you differentiate, multiply, differentiate, multiply, differentiate, multiply, like that. So now the problem has been converged to differentiation, multiplication, and then addition. If we can do that on actual hardware, we can build this controller. Okay, so the US is actually in the control signal. On the right hand side, what you have is not the control signal, but rates of change. First derivative of US, second derivative of US, third derivative, like that, all the derivatives. But on the left hand side, you have the actual control signal, US. So that is why we call this kind of equation an infinite impulse response filter, because it takes two inputs. One is the error, the other one is the rate of change of the output. The first derivative, second, third, fourth, like that, high order derivatives are also going into the controller as input. Even though you can't see it over here, it's happening inside the controller. I think I have said this earlier also. What you see can be can deceive you, right? If you don't understand it properly, we can't actually draw everything that we do mathematically. We can't draw. These block diagrams are very, very simplified illustrations, aspects of what we actually do in mathematics. So some of these feedbacks are actually inside and we don't see them there, right? When we write down in Laplace equations, sometimes the actual signal flow gets concealed, hidden. Right. So now I'm going to show you how you can draw this equation like this. Right. This is the implementation structure of the controller. You can see the error here. Error gets multiplied and then error gets differentiated, multiply, differentiation, multiply, differentiation, multiply, differentiation, multiply, like that. And all the terms are added together. And when it comes over here, it is the signal, this whole braces and this ES, this part is there. Okay, this part is there here. And on the other hand, this is your output or control signal, and you get it differentiated and multiply bn minus 1, right? Over here, the control signal gets differentiated and multiplied, differentiated, multiplied. So it happens like the differentiation. So this is the differentiation channel, successive differentiation, and every time, every step, you multiply it with a gain and add together. So when you add all of these terms here, you bring it to the summing point as negative because of this negative sign. Okay? So the result is actually the control signal. Now, we know with a very high degree of clarity what's happening inside a controller, analog controller. To implement this one, right, we need to be able to differentiate signals, multiply signals, add signals. Okay, these are things we need to do. So my question is, how can the controller be physically implemented? The answer is, can be built with op-amps. You know what an op-amp is? Op-amp is an electronic circuit, comes as a chip, integrated circuit. This chip is designed to do just this, that is arithmetic and calculus, both in one hardware chip. You can use the op-amp to add signals, to multiply signals, to differentiate and integrate signals. By the way, that is why it is called operational amplifier. This operational means mathematical operations, right? Op-amp. So now you can actually integrate the electronics into the theory, mathematics, right? Because these two go hand in hand. When there's a need to implement arithmetic or just mathematics in general on real hardware, the electronic world has to provide an answer for that one. Electronic engineers, the researchers will have to work with mathematicians and how to realize this one. So it was very easy because engineers are part of mathematicians, physicists, all one group. So therefore, things can be easily done there. Okay, right. So I'm going to show you this one. This is the most familiar operational amplifier, LM741. I think anybody who has done basic electronics would have seen this, would have gone through this, would have used this one. It has 8 legs and it's a dual input device, which means it has a positive supply as well as a negative supply. You can see it pin 4 and pin 7 power supply. And also it has 2 inputs, negative and positive input, inverting input and non-inverting input. That is how we call it. And you can use this IC. You can have many of these ICs in your circuit to implement, design and implement circuits to do mathematical performance, right? Operations rather. So I just want to show you the inside of LM741, right? It's not just one unit, it's a circuit inside. You can see a lot of transistors, right? Resistors, a lot of connections, right? And also the terminals. You can see here offset null, terminal 1. That is this terminal 1, right? And you can see non-inverting input number 3, terminal number 3. This is the non-inverting. Terminal 2 is the inverting terminal, right? Inverting input over here. And you can see here the power supply, negative is 4, and positive supply is 7, and output is 6. So you can see it over here. Terminal 6 is the output. This is where you take the signal out of this. So 2 inputs, 1 output, okay? Take a little time, right, to look at LM741 internal structure and all, right, and study a bit about it. Not too much. Now, I want to show you some basic things. This is not new for those who have done electronics, but others who have not done it may be a bit difficult to understand. So that is why I thought of giving you some a primer in op-amps, not much, right? And I asked you to read a chapter or two on op-amps, basic theory, basic circuits, and get yourself familiar with the contents, right? So here you can see one circuit, this one. How you use an operational amplifier, let's say LM741, right? And you connect it this way. You have a signal that you want to amplify, right? This is how you use the op-amp to do that. So you connect your signal, VI is your signal, okay? Let's say error, this is the error signal. And you want to multiply it with a gain. So we have that already here. We have the error, we want to multiply this constant gain. How we can do that electronically? So let me show you this. We connect the signal to the positive terminal or non-inverting terminal. We call it that way. You will understand why we call it soon, right? And this is the other input, which is the inverting input terminal. We connect it to the ground through a resistor R1, okay? And the same terminal is actually connected to the output terminal, that is V0, through another resistor R2, okay? This is a very simple op-amp circuit with 2 resistors, 1 input and 1 output, right? So when you deal with op-amps, right, you have to draw the equivalent circuit for the op-amp. So there you don't draw the op-amp or whatever, but all the other components like this. This is an equivalent circuit for the op-amp positive gain. So before we can draw the equivalent circuit, you need to know 2 principles about op-amps in this particular discussion. When you use op-amps for arithmetic operations, right? The internal arrangement of the circuit, this one, does not allow significant difference between the 2 input terminals, the voltage between the 2 terminals. It does not allow, it doesn't like it. So therefore, we assume that there is no voltage difference between the 2 terminals, right? When we draw the equivalent circuit to simplify it without compromising the accuracy too much, we make 2 assumptions. One is there is no significant voltage difference between the 2 input terminals. So 0 volts between these 2. This is the first assumption. The second assumption we do is that the op-amps are made with very high input impedance. The circuit has a very high input impedance, which means it does not like to take any current into it, doesn't swallow any current. So therefore, even if you connect a voltage here, it doesn't mean that you push any current into the circuit. The op-amp doesn't like to take any current. So the current that goes into the op-amp is 0. We assume it to be 0. Actually, it's not 0, but very small because of the very high input impedance. Okay, the two assumptions. With these two assumptions, you can actually draw the equivalent circuit. When these two terminals, when there is no significant voltage difference between these two terminals, which means when you connect a voltage to one terminal, the internal electronics will make sure, will raise or lower the voltage of the other terminal so that they are equal. This will happen, this adjustment happens internally so that the voltage difference between the two terminals will be insignificant, right? So therefore, when we draw the equivalent circuit, we do not draw two terminals but one point, as if these two were short circuited. Okay, short circuit like this, one point, because the same voltage, because these two are same voltage. There's no current going into the op amp, so therefore current is 0 amps. Okay, and then from this point you have a resistor and a connection to the ground, and from the same point you have another resistor R2 connected to the output. So this is a very simple circuit. Now don't have to worry about op amps now. Solve the circuit. So you can write KCL, Kirchhoff's current law, right, to this point. Current coming in this direction, current coming in that direction, current coming in this direction. When you add all these things, should be equal to 0, because that is what Kirchhoff says. If you look at a node of a circuit, all the currents coming in all the branches, currents that are coming are positive, currents which are going out are negative, right? So with that sign convention, when you add them together, it's 0. In other words, you can say current coming into the circuit is equal to the current going out of the circuit, either way, right? So if you are at this point, you can see there's a current going out of that point, which is say V out and V in. The voltage at this point is, by the way, V in. Okay, so this point is, if you want to calculate all the currents coming into the circuit, you can say into this point rather, V out minus Vi divided by R2, which is equal to what? Vi, that is voltage at this point, minus this voltage which is ground, divided by R1. Okay, so it's like there's a current going like this from V0 to the ground. So V0 minus Vi divided by R2 is equal to Vi minus 0 divided by R1. So after that, you can simplify this one and figure out this one. V out, output is equal to R1 plus R2 over R1 times Vi. So input, output, and this is the multiplier or the gain. Understand? So this circuit is actually a positive gain. It multiplies the input signal by a factor and produce that voltage at the output. Positive gain. Now, if you look at the negative gain, if you want to amplify a signal, but in the same time you change the phase, right? Positive to negative or negative to positive. You connect the signal to the other terminal through a resistor and take another connection from that terminal through a resistor and connect it to the output. And the positive terminal or non-inverting terminal you connect directly to the ground. So when you do that, you actually pull down this terminal to 0 volts like this. Okay, so therefore voltage at this node also 0, because internally op amp will make sure that there's no voltage difference between the two input terminals. So it will be 0 volts. And there's a current from Vi to that terminal, but it doesn't go into the op amp, it goes the other way to the output. So you can draw the circuit like this, equivalent circuit. Now when you write down the equations, you can say Vi over R1, that is Vi over R1, because it's 0 volts, right, is equal to V out over R2 minus. So V out is actually coming into the circuit, into the node, right? So when you write it down, you have to write it like this direction. So it is going from here to here. So when you simplify, V out is equal to R2 over R1, R2 over R1 times VIS with the negative sign. So you amplify the signal, but with a negative sign. Okay. So there are other circuits also. This is a differentiator. If you want to differentiate and multiply, you saw the multiplication here, right? But differentiation, it's like this. If you want to differentiate a signal to get the rate of change of the signal, you connect the signal to the op amp through a capacitor. And the negative terminal, right, is connected to output through a resistor R. Now, if you draw the equivalent circuit, again, you can see there's no voltage difference between the two terminals. So it is just 1 point in terms of voltage. And because the other terminal is connected to the ground, the voltage at that point is 0. We call it virtual ground, right? Virtual ground. Even though this point is not connected to the ground, it will have the voltage of the ground because of this connection, other terminal connected to the ground. So we call it virtual ground. And on one hand, you have the capacitor and the signal. On the other hand, it has the resistor and the output. Now, if you write the equations again, KCL for this node, what is the current through a capacitor? Current through a capacitor is capacitance times rate of change of voltage, dVi over dt. That is the capacitor equation, right? Plus, if you look at the other side, right, this time you are adding voltages, currents together and set it to 0. So it is V out divided by R, V out divided by R equal to 0. Once you simplify, V out is equal to RCS VIS. So S means differentiation. So you differentiate and there's a gain also, RC, with a negative. So it's a differentiator and in the same time inverting amplify. It amplifies with a negative sign. So if you want to have a positive gain, you can have this negative gain, right, connected with this one together. So these small blocks, you can have so many of these blocks cascaded together to make positive gains, negative gains, differentiation and multiplication with the positive gain. So you can do whatever you want by selecting RC components accordingly. So take a little time to figure out this one. Take 2 minutes or 3 minutes, write it down. This is adding two signals together, because in your circuit, you can see you need to do this addition, okay? Plus, plus, or plus, minus, or whatever. You can say plus, because if the signal is negative, then you just need to do addition here, right? So how we electronically implement that? It's over here. Take 2 minutes and figure it out, okay? Okay, Now, I just want to check with you whether you have understood this one. So, before we get going any further, Rumesh, can you figure out how op-amps are used? Yes, go ahead. Is it clear to you, Rumesh? De Silva, is there anything that is not clear to you here?
No, sir, everything is clear.
Right. Kalana Gunasinghe, what about you?
Yes, I understood the one in the presentation. Yes, sir.
Is there anything that is not very clear to you?
Sir, can you hear me?
Yes, go ahead. Is there anything that is not clear? We lost him. Hey, Rath, how is your connection? Hey, Rath, is there anything that is not clear to you?
Yes, sir.
Clear, right? Right. Mustafa?
Yes, sir.
Okay. Gunasekara?
Yes, sir. Clear.
Right, right. Okay, I think it's clear to all of you. Now here is the addition. You have two signals, V1 and V2, and you send them through two resistors into the non-inverting input, right? And then connected it through another feedback resistor R3 to the output. And while it is happening there, on the other side, the non-inverting input is connected to the ground through a resistor, and there's another feedback resistor R5 connected the terminal to the output. So then when you draw the circuit, it will look like this, right? And I don't want to take time to get you through this process. This is pretty ordinary stuff, right? And eventually you get this equation. Now, so now after this point, this is still not the adder. It's not the adder yet. You have to make it an adder circuit, right? This is what you get. To make it an adder circuit, you do some assumptions, right? From here, that is, you select the resistors R1, R2, and R3 to be equal to each other, right? That is R. So which means this is R, this is R, this is R, right? So that is why you add V1 to V2, right? You can add V1 plus V2 over R because R1 is equal to R2 and it's equal to R, a single resistor. The V3, so V out actually, you don't add it there, you keep it separately like this, 1 over R V out. And also this one is 1 over R1, 1 over R1, R2, 1 over R3. This whole becomes 3 over R, just like this, 3 over R. And the rest follows like this. So when you do further assumption that R4 is equal to R, this one is also R, and R5 is equal to 2R, right? Then you make it like this, eventually like this, right? So it is the adder now. V1 plus V2 is equal to V out. That is how you use an op-amp to add two signals together. This is in Laplace. So when in Laplace, the two signals are adding together, the same thing is happening in the time domain. There's no difference there, right? Simple addition. So there are integrators also. I don't want to take it any longer. This is the error signal. Can you make it for me? Can you write down the equations? Now, earlier, I showed the equations and asked you to digest and tell me whether you understood it or not. And this time, an exercise. This is the error signal. If you want to calculate the error, right, the difference of the two signals, This is how you do that. You have the two signals V2 and V1, right? And I have drawn here the equivalent circuit also. Can you write down the equations and get the final error signal equation? Please take a couple of minutes. All right. So let me show you the process here. Now you can check with what you have done. It is pretty obvious, so I don't want to explain too much here. You can see the same point here, right? Both terminals, they have pretty much the same voltage. So let's call it V and V. You have to put a value there, right? Because we don't know. You can't say it's 0. Right? We don't know it. Some voltage V. And using that voltage, you write down the KCL for this node here, right? V2 minus V over R2, V0 minus V over R4. So this part here. And this voltage is a potential divider circuit here. So V is V1. If you look at V1, if you look at this part here, this is 0. This is some voltage. This is V1. From V1 to ground, it is R1 and R3. So it is R3 over R1 plus R2 times V. So that is how you calculate the voltage at this point. When you have voltage V1 connected to this point through a resistor R1 and then connected to ground through R3, this is a potential divider circuit. You can calculate the voltage here. You can do that because there's no current going into the op amp. That's why. Okay. So then you continue the derivation. Eventually, what comes out is R4 over R2. Where's R4? Here. R4 over R2, right? V1 minus V2. The difference of the two. So if you want to get actually the difference of two signals, like over here in your control implementation, the summing point plus minus, you can do it like this. So therefore, everything that we need to physically implement an analog controller is possible using op amp. But there can be, depending on the complexity of the equation, right? If you see this equation here, every differentiation has one op amp, right? So many op amps there, right? If you look at this one here, every S block is an op amp. So it's here. And every gain is an op amp. Every summing point is an op amp. There's so many summing points. And the error signal calculator is another op amp. Likewise, it can be some 20, 30, 40, 50 op amps on one board. But it doesn't mean it is too complicated because it is just a repetition of the same block again and again and again. So it's electronic design is pretty easy and simple. Okay. Right. Excellent. So now let's go back to the controller that we designed earlier. You remember that. This is the servo loop shaping exercise we did extensively and we designed to a given specification, remember? The bandwidth, phase margin, steady state error, that kind of thing. And this is the controller we got, 129.3 gain to open the bandwidth to 20 radians. I remember that. and the lead compensator to get to, I think, 45-degree phase margin, right? And then in order to improve the steady state accuracy, we design a lag compensator. So all these three blocks is the controller. Now, if you write down the equation for the controller, US over ES, US is over here, ES is over here, right? You cascade these three blocks, S plus 0.95 over S plus 0.01, 0.1 rather, that is the lag. Then 1.85 times this one is the lead compensator, and 129.3 is the bandwidth opening gain. So when you simplify this one, you get to this rational polynomial of S. So this is the numerator polynomial and this is the denominator polynomial. Okay, they are equal in order. Now if you cross multiply and isolate US on the left hand side and bring all the other US and ES terms to the right hand side, you get this one, isn't it? So this is a very clear execution of the theory that we just learned. Okay, now you have to tell me how to implement this equation, right? So I want you to draw this diagram now. For this diagram, right, for this equation, this is the controller you built, not I built. You built this controller, right, together with me some time back. So write this equation down. Right, write this equation down. And I'm going to pedal back. Can you draw me this one, the analog control implementation, the control implementation structure, and identify how many S blocks you need, how many gains you need, what are the values of these gains, and all. Can you draw the controller structure? Okay, so we're gonna get a little break now, about 10 minutes, right? Or maybe a little more than that. If you want to do this one also, maybe 15 minutes, right? Prepare your controller implementation, this structure, right, for this equation. This one. Are we clear? Any questions before we take the break? So is the assignment clear? Now this is uh, class exercise. Sachit Ratnayaka, is it clear to you what I want you to do?
Yes, sir.
Okay. Mimanagi, is that clear to you?
Yes, sir.
Okay. Nasif?
Yes, sir, it's clear.
All right. So then let's get started. This is the controller we developed and we want to draw the block diagram, rather controller implementation structure. With this one, we are one step closer to the final design. After that, we can replace these blocks with op amps. Okay, and we know the op amp circuit. That is the hardware implementation of the controller. Okay, so let's take a break also together with this class assignment, and we'll take about 15 minutes for both. All right. So let's see. This is the controller equation. Right. You can see ES error gets differentiated 2 times and gets multiplied 3 times. Okay. And US gets differentiated 2 times and multiplied 2 times as well. So this is the structure. This is the error coming into the circuit, gets multiplied 1 time, 2 times, gets differentiated 2 times, and then 64.6 over here. This 64.6, you can place it over here. And US gets differentiated 2 times and multiplied 2 times as well, added together. That's it. Now, if you want to draw the circuit, electronic circuit for this controller structure, what you want to do is to replace these S's, differentiators, right, with actual differentiator. Where is that? This one, differentiator. So for every S, you put one of these. But you have to be careful of the, when this is differentiating the signal, it also multiplied it. So you have to adjust that also, right? And also for every gain you have here, these are gains, right? These are gains, 1, 2, 3, 4, 5 gains. You have to put positive gains. But again, be mindful that sometimes when you have a different, say, negative gain, then you need to have another negative gain to make it positive gain, right? So these internal adjustments you have to do, but basically, conceptually, it is just substitution for every gain, every differentiation, one of these blocks. So when you do that, this particular circuit will look like this. All right, this is how you get the gain, 10.26, and the differentiators, right? They come in pairs of op-amps, because when you have one gain differentiator, it has a negative gain also, so you need another negative gain to make it a positive, right? So that's what I said earlier. Differentiator is not just what I showed you here. Because of this negative RC gain, you need to have another negative gain, one of these, to make it positive. Okay, so that's why you get 2 op-amps in one differentiator, like this. So I want you to do a little homework. You will get this lecture note, and anyway, the chapter is there. Try writing down yourself. Get a big paper, A4, right? Start from one corner and keep drawing, right? Keep drawing this controller and try to get this one. So after that, it's very easy to actually make this controller, right, as a one single electronic board and connect it to the system, and it will perform exactly the same way it would have anticipated, right? So that's about it for analog controller. Any questions, please? No questions? Okay. So let me then start the next chapter. Right. So as I mentioned you, earlier, the digital control is uh, a different way of implementing the analog controller. Uh, if you look at okay, what is digital control? How is it different from analog control? Right? You will get most of the answers on the fundamental difference, because analog means continuous time, digital means discrete time. So it is just mathematical difference between the two. Yes. Then, because the differences in the mathematics, these controls are based on, the electronics is also going to change when you try to implement. What you saw up to now is usage of continuous time electronic component like resistors, caps, op amps, all continuous components, right? And the circuit. Now, when you have digital controls, you are not going to use the op amp, the transistors anymore, right? The way you use it, but now you are going to use the discrete version of it, discrete components, right, to implement that. So the discrete components are also made of analog components. Remember that, okay? But it doesn't matter. We don't want to see what's inside, but the way it operates is discrete. So you need to understand the fundamental difference between analog or continuous time and digital discrete time. If you can understand the fundamental difference, there won't be any other issue here to understand the difference between analog controller and digital controller. So that is why this lecture is titled as Digital Implementation of Analog Controller. To tell you that digital controls means actually another implementation method of analog controller, right? It's not a completely different thing. That is one thing. The second thing I want to tell you is that when you are in discrete time, it's like you operate in very brief periods of time, okay, and then you go to sleep for some longer time, and then wake up and look at what's happening and take decisions and put decisions into action and so on and so forth within a small period of time, and then go back to sleep, and you sleep some time and then wake up again and look at what's happening, what has happened, and you take your decisions and put the decisions into action and then go back to sleep. It's like that. It's like that. That is digital control. Let's say you are running a company, right? Maybe 5, 6 companies, right? Every day you visit this company and check the situation there, what are the problems, and you take decisions and ask people to do this and that, and then you go to the next company, do the same thing, go to the next company, do the same thing, like that. and you go following day, same routine. You go to the first company first and check what has happened as a result of your decisions the other day and make some additional adjustments needed. And you spend the second day very much the same way that you spend your first day. And you go to sleep same night and then come back again, third day. So this is discrete control, digital control. If you do anything like that, you are doing digital controls. Okay. Now, analog control, even though we didn't specifically mention, when you say this continuous time, it's happening all the time, which means you have a company and you are the owner of the company, you are there. You don't leave the place even for a single moment, right? You don't do any other jobs. You stay there 24/7, right? All 365 days a year. You never keep your eye away from the company. You are there, you monitor everything, every moment. So that is continuous control. Now, if I put that example and ask you the question, which one is better? You would tell me, of course, the first one, analog control or continuous time. Yes, it is. Because you don't miss anything. In case of the discrete control, if you look at the company and whether the people are there, whether they are working or not, right? After that, you are not there for the rest of the day. So people can do various other things. When you come back following day, things may not have happened the way you expected, would have expected, right? So because there is a significant time, right? System is running without your supervision. That is the very nature of discrete control. Unattended period is very high. On the other hand, the whole world is transforming from continuous time to discrete time because of the other benefits in discrete time or digital controls. Continuous time control is very hard. As you can see, you can't stay there in your company, right, 24/7 and all 365 days a year, right? Then you are stuck in that small company, whatever it is. You won't be able to do many other things, right? So therefore, it's not good. I'm just comparing on conceptual basis, but there are more technical reasons as to why we move on to digital controls, right? Now, in working in continuous time is hard when it comes to electronics because working with the op amps, resistors, and cabs is difficult. It's difficult. So when you put them in the discrete time, you use digital controllers like Arduino, Raspberry Pi, computers, STM board, whatever it is, digital electronics. Digital electronics come with software also, right? The op amps, they don't come with software configuration. It's a hardware configuration. You have to change hardware. You have to build it from scratch. And if there's any change, you have to do it again on the hardware. Changing hardware, soldering, desoldering is very hard thing. But digital controls come with programmable electronics, right? Uh, you have the software interface to the controller. You can design your controllers, change the gains, do a lot of things in your programmable environment. This programmability is key to digital controls, right? Therefore, you can change, modify, update. You can do so many things in your controller, right? And people like it. It's very convenient to do it that way. Now, uh, electronics has developed very significantly over the last decade, so that even though we say discrete control is unattended time between the attended time samples is long, it's not so now because we have very high-speed processors at affordable price. We can have these samples very closely apart, which means every second you can read the control system at least a couple of times. Or in fast mechatronic systems, you can have 100 hertz, 200 hertz, 1000 hertz, okay, few kilohertz sampling intervals, which means like analog, very close to analog, right? If you look at the plant 1000 times a second, you can reasonably say analog control, very similar to analog control. So there won't be anything that you miss significantly, okay? So because of these reasons, there are so many, right? I recommend you read some documents on the internet on continuous time control and discrete time control and learn a lot, self-learn, just read, common sense, everybody can understand. So that is why now discrete time control, digital control is a very affordable way for controller design, right? So having said that, let me show you how you can build the same controller in the discrete version, okay? So earlier you build the circuit in analog, continuous time. Now I'm bringing you through the other route and try to design a discrete controller. Okay, so rather than telling you the theory, teaching the theory, if I show you how the process is conducted, you can understand a lot of things. Anyway, the next semester we'll have digital control. There we go deep down into theory, discrete mathematics, and learn a lot of things. But even without that, anybody can understand some basic stuff. So here is the controller again. Okay, the controller equation, and finally the controller structure, right? Now all what we need to do is to replace the analog controller with discrete approximation. That is how I call it. So I see discrete controller as an approximation to analog controller, right? So then it is actually something, say, a part of analog controller itself, because I know analog controller pretty well now. So who is the close approximation for that in the discrete domain? So that is what I'm going to develop here. So I first want to modify the circuit before I can bring the discrete controller. So what I do is this. So look very carefully, right? I want to get the output, the feedback, IS, not this continuous manner. This is just wire connected to IS. So every split moment, right, nanosecond, right, you see it immediately over here. But now it's not like that. It's like this. You have the response, YT, and there's a switch which is normally open so that you don't see the change over here. Whatever happens to the output, you don't see it immediately here. Just like what happened here in continuous control. So now, whatever happens to YT is not being observed until this switch is closed. So this switch is closed at regular intervals. If you say 1 hertz, one time every second it closes, and at that moment you will read the response. So let's say you have this switch operating 1 millisecond and 1 hertz sampling interval. So which means every second it closes for 1 millisecond, and during that 1 millisecond you read it, and after that for the rest 999 milliseconds you don't know what's happening, and after exactly 1 second you read what is there. So therefore you are missing the profile of YT, the profile curve and all, right, for 999 milliseconds. And after that, whatever value YT has attained finally is actually read in the final 1 millisecond interval. So that's how it works. So therefore, it's like you are connecting a switch. Okay, connecting a switch. We call it a sampler. Right. This is the first device you are going to introduce to the system. If you want to build a discrete controller to the plant, right? And the second thing is that the input here is RS. Input here is RS. But now, because you're operating a discrete controller, we call it RK plus 1, RK plus 2, RK plus 3, RK plus 4, like that. It's not a continuous value. You can have a continuous value, but anyway, what comes to the system is discrete samples of that waveform. Okay? If this is operating, the output is operating at 1 hertz, this also has to be operating at 1 hertz. Every second you command, okay, this is the reference, this is the reference, this is the reference. Every 1 second, for a brief moment, you command the controller, this is the reference value. Even if you keep it continuously, doesn't matter, but the controller will take it only once every second. So now, because these signals are all discrete signals, the controller also has to be discrete. Now look at here, the controller is CS. S stands for the Laplace, right? Continuous time, Laplace transform. And here it is CZ, which means discrete domain, and it is Z transforms. So this is another thing you need to remember. Just like we have Laplace transforms dealing with differential equations in continuous time, we have a tool very similar to that called Z transforms to deal with discrete signals. Signals that are not continuous are actually processed using Z transforms. Okay. So now we have the two worlds, continuous time and the discrete time. Continuous time, we have Laplace transforms. Discrete time, we have Z transforms. Continuous time, we have continuous signals. Discrete time, we have discrete signals. A discrete signal is something like this, RK. Okay. Whereas continuous time is RT. You know that. Now in continuous time, when you try to model a plant, you get a differential equation. This is the most important thing I'm going to tell you. In continuous time, when you try to model a plant, you get a differential equation. if you try to model a plant in discrete time, you don't get a differential equation, but you will get a difference equation. Difference equation. Okay. So these are the whole system that you need to know between continuous time and discrete time. Now, the last thing I want to tell along these lines is that you are not going to develop the difference equation directly from the plant. What you're going to do is to develop the difference equation of the plant using the continuous time controller, which is already available here. The controller is available. You have developed it in continuous time. So you don't need to develop it again for discrete time. You take this one available controller and convert it or transform it to discrete world. This is why I said to you, we are not actually doing something totally different here. We are approximating the continuous time controller with a discrete time controller. Okay. And in order to for the discrete time controller to function properly, you have to make your reference signal and the feedback signal all discrete. And that is why you attach the sampler here to make your output discrete. Understand? So this is how rational this whole process is. These are not arbitrary things. Very well thought of, very well designed process. Okay. So again, we take the controller continuous time and approximate it with a discrete version of it. And you take the output or response through a sampler to make it a sampled signal. Reference is anyway a data file, a sampled signal anyway. And the error signal is also a sample signal now, because these two signals are sample signals, discrete signals. Controller is anyway now discrete. Output is UK. It's also discrete. So we are changing the signals and the controller to the discrete versions from their analog signals. Okay. Now there's one little thing remaining. What is in between the plant and the signal, control signal, UK, discrete signal? ZOH. We call it zero order hold, or you can say first order hold, second order hold, whatever it is. It's a holding circuit. Why? You are controlling the same plant. You are controlling the same plant. Not even nut or bolt has changed from the plant, right? It is the same plant you are going to control now with the digital control. So therefore, plant is not going to change. It is GS. You can have GZ, the approximate version of that. But I think it's more logical to keep it like that, GZ, GS. Which means this plant can take only analog signals as the input, which means UT. The plant can take only continuous signals, UT. But now what we have is UK, because your controller is discrete. So now you need to do this. Convert UK to UT. So what is UK? UK is a sample signal. UT is a continuous signal. So you want to make a discrete signal into a continuous signal, and the device you use for that is a holding circuit. So the simplest holding circuit is zero order hold. So when you bring that also into the plant, you have the analog actuator and plant, but digital controller. Digital control. Is there any question about this? Is everything clear to everyone? Let me ask from few of you. Vigetaran,
Yes, sir. It's clear.
Vikramathilaga,
Yes, sir, it's clear.
Kapetipola, Kapetipola, are you there? Ratnayaka, Ratnayaka, are you there? Veera Singha,
It's okay, sir. It's clear.
right. Seon,
Clear, sir.
right. Herath,
Yes, sir.
okay, fine. So I think it should be very clear to you. These things are to be understood rather than to be remembered, right? So things that you understand, you don't have to take effort to remember, right? Things that you don't understand, you have to take effort to remember. So that's why it is very tedious to remember things, especially when there are so many of those things, right? The fundamental concepts you cannot remember, you need to understand. Okay, right. So following up, I will show you the sampler and zero the hold, because these are the two components that you bring into the plant, right? The sampler here and the zero the hold. Sampler and zero the hold. You need to know about these two circuits, and then you need to know about how you can uh, develop a discrete version of your analog controller. So these are the blocks that you need to learn about. Then you can put things together. You have a discrete controller. Okay, right. So sampler, there you can see yt and yk. So this is yt, the continuous signal. It goes like this. And then you take the red arrows, the samples you are taking at regular intervals. The red arrows, right? These are set of numbers. That is yk. This curve is not a set of numbers, right? It is a curvature, waveform, and that is yt. So you convert a waveform into set of numbers here. Okay. So after that, you are dealing with these numbers. You are not talking about a waveform or any curvature. You're talking about these numbers. It is just a game with numbers. So let's say if you want to say this is the first sample, it is y0. This is the second sample, that is y1, y2, y3, y4, y5, y6, like that. Okay. So it is a sequence of numbers, no waveform, nothing. And also you have to say, okay, what is the sampling interval between these two? Say k y1 to y2, what is the time? That is the sampling interval. So once you specify, okay, my sampling interval is 1 second, and then you can talk about the samples y0, y1, y2, y3, y4, right? In the discrete version, this capital T sampling interval does not appear all the time. Only briefly, where you talk about sampling interval, it comes there and it goes to the equations, different places. After that, you don't see it. You don't see any time equation. You see K, this one only. K equals 0, K equals 1, K equals 2, and so on. So between K equals 1 and K equals 2 is the sampling interval, right? But it is not written all the time. It is recorded and used for basic equations, and after that it's gone. is entirely k, right? When k changes from 1 to 2, 2 to 3, 3 to 4, like that, how the plant changes its response, right? Then the other graph right below that is zeroed whole. What is that? Let's say you have uh, ut. So this is ut in your continuous time controller, right? So nobody is calculating these values and put it there, because the op-amp based controller will change the signals as the input signals change immediately almost. So therefore we are not talking about numbers there. It's a waveform signal, right? So it goes like that. Now if you want to get samples out of that, right? So sorry, the other way around. This is zero to whole. There what you do is you have samples you calculate from your discrete controller, right? So this is a sample, this is another sample, this is another sample, and so on. So the zeroed whole circuit over here, what it does is it receives UK, it receives these values, okay, from the discrete controller. And in between, it will maintain the same value. You keep the same value there until the controller sends you another value, like over here. Until CZ sends you a new value, you're going to keep the previous value as it is. So it is flat top. That is why we call it zeroed whole, flat top, like that. Okay. Any questions about the sample and zeroed whole, please? So you need one of these at the output over here, response. You need one of this between the controller and the plant, zeroed whole. Okay. Now let's look at the controller discretization. So as I said to you, you need to have the sampler, zeroed whole, and then you need to develop discrete approximation to the controller, CS, right? Which means you have to derive CZ from CS. So we are now at that stage of development. So let's see. This is our controller, CS, continuous time, US over ES. This is a rational polynomial, right? And then if you do this in the transform into continuous time, this is what you get, right? You do the cross multiplication and inverse Laplace. So then you get this B0 times S to the N means nth derivative of ut. And then you have B1 S to the N minus 1, which means N minus 1th derivative of ut multiplied by P1, and so on, right? On the right hand side also you see error times A0 S to the M, which means mth derivative dmet over dtm, mth derivative of the error es multiplied by A0, goes like that. So now if we can replace this derivatives, first derivative, second, third, fourth, and so on, with their discrete versions, we are done, aren't we? So I need an approximation for the first derivative in continuous time, second derivative in continuous time, and so on. Okay, so that's all what I need. The equation tell me you just need discrete approximation to the derivatives. That's it. So the discretization of a continuous controller is actually the discretization of the derivatives in the continuous time. So this is what is called breaking the problem into atomized problems or atomic problems, right? To figure out what exactly is the problem here, right? And then you solve it, the whole thing is solved. Uh, the target or the goal to achieve something, right? Um, it conceals the actual goal. Actual goal is hidden inside the visible goal. So the actual goal, if you can achieve, the visible goal is anyway achieved. So the visible goal here is this one. But when we dig deep down into the problem, we figure out the actual problem. It is just this. If I have a solution, a discretization method for differentiation, I'm done. Okay. So actually it is not a big deal. It's not a big deal. Why? So I know how to calculate different derivatives in discrete time. Everybody knows it. Now let's say this is my curve, continuous time curve, and I take samples like that. This is my time, right? At the kth moment, I have my time kt. Then the sample uk at that moment. A moment ago, it is k minus 1 times t, one sampling interval prior to that. And my controller should have given me uk minus 1, right? And another step behind, 2 steps back, k minus 2t, controller would have given me uk minus 2. So this is how the controller should operate, okay? Every capital T time, it has to uh, produce a signal. It has to give out a control signal, okay? Now, if you use Newton's backward difference method, right, here, I can approximate ut to uk. What about dut by dt, the first derivative? First derivative, the way I calculate is uk minus 1. So this one minus this one. Signal has changed from here to here within time t. Say divide by t. This is how I actually calculate the rate of change in the discrete version, right? Digital. Now here you can see it's not actually one rate of change. It is going through a range of continuously varying derivatives, right? So if you look at the rate of change, is one value here, another value here, another value here, and so on. But in the discrete version, is only one. There's only one rate of change. That is the difference from here to here divided by time. So this is the approximate version. What about the second derivative? Second derivative, I ask you to do that yourself. I think it's no big deal again. This is the first derivative at k. And what about the derivative here at k minus 1? You can write it down again. And then take the difference of the two and divide by t again. So then it becomes t square in the numerator. And this is the second derivative. Please do that, right? If you have forgotten this discrete calculation for rate of change. And you can go on for higher derivatives, okay? Similarly, error. This is ut, this is error. If you want to calculate the error rate rate of change of error, rate of change of error, right? These are the equations. So I have done it for second derivative. You can continue for third, fourth, fifth, or whatever derivative uh, as it is in the equation. So therefore, the controller is a function of uk minus 1, uk minus 2 up to uk minus n for all the derivatives of uk, right? Plus the control signal now. And on the right hand side, right, is this side, the error terms. So there you have error rates, right? They are discrete versions. You can actually figure out what is UK, right? That is the control signal at time k. So this is how it works. This is how it works in discrete controllers or digital controllers. So you might be a little worried here because we are not actually taking a lot of information from here to here, because in discrete version that information is not available. So therefore you can't use it for very close controls. Continuous time means very, 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 very close control. Every moment you keep an eye on it and make the corrections, because it's hardware correction. My hardware is very, very fast. Now, here, this is software correction and eventually implemented on hardware. So therefore, there is a time between samples where you don't know how the signal has changed, right? But you do the correction at the end of the sampling interval, looking at the overall or average rate of change. So these are all averages, right? Not the actual absolute rate of change. Now let's take the controller we have at hand, right? But I think this is the same controller we were using. It looks like that, but it doesn't matter. I think it's the same controller, right? I would have done this as a class exercise because you can learn a lot of things by doing, not just listening to me. Even the small things, I want you to pen it down, write it down. You will understand it. So I think I need to give this as a homework to you, class exercise, right? Rather than telling everything to you like spoon feeding. I don't like it. So why don't you take down this one, digital controller. This is the controller, right? This is the controller, 0.27 d square ut dt square plus 10.3 dut dt ut, like that. This is the error signal. This is coming from a continuous controller. So I want you to replace these derivatives, differentiations, right? dut over dt, d2 ut over dt square, first and second derivatives using their sampled signals, uk, ek, etc., right? And develop the discrete equation. Develop the discrete equation. So take down this part here, right? And send me by email, right, your discrete controller, your discrete controller. I want your handwritten ones. You don't have to type it on paper, taking time, right? But clearly write it so that I can read it, okay? And then get a photo of that and email it to me. Because if I just walk you through the process, you might easily forget it. All right. So I think yeah, we should wind up today at that point, giving you time to work it right and submit to me. Because if I continue, I will be telling you the answer. Right. Any questions so far?
So what is the deadline for submitting?
Before the next class. Before the next class. Usually when I give you assignments, unless I state otherwise, it's 1 week, within the week before the next class, because most of the uh, uh, assignments given I discuss in the following week. So I want you to submit answers before that. Okay, so I will do it this way. I want you to um, I want you to design the analog controller structure for this one. Analog controller structure for this one. And the digital controller also. Right? It's something you have done it. I have already explained a lot of things. But I want you to write it again and develop the new content I haven't taught you yet. Right? And then prepare one report. Okay? So one is the analog controller implementation, right? Analog controller implementation using the op amps. You draw the circuit. And the second one is discrete controller, right? As an equation. There's no implementation structure for discrete controller because it's a piece of software that you program onto a microcontroller. Okay, right? So this is an assignment for the week, and email me your assignments and make sure your subject title is ME5144 assignment 1. So I'm writing it in the chat box, ME5144 assignment 1, and put your index after that. Okay, so this is the subject for email, right? So do it like that.
So excuse me.
Yes, go ahead.
For us, the subject code is given as EN5001.
All right,
So is
I
this a
forgot that. Yeah, so EN5001. That's the code.
so is this a mark assignment?
Yeah. So this one is take home. You have time to work it out. So it will be given marks. Any other questions, please? Yeah, one person has the microphone issue so that he cannot respond to the questions. Fine, but you better get microphone fixed. Okay, right. Okay, so if there are no more questions, we'll wind up today. And please make sure you submit your answers to me before the next class, right? That is next Sunday. Okay, then. So that's all for the day. Thank you for joining in.
Thank you, sir.